Hello, greetings. Today we're going to have a look at the product rule, and to begin with I just want to do a little warm up to get the brain in gear. We're going to have a look at this formula in front of us and solve it, and we're going to find the derivatives of it. Okay, if you've got this nailed down you can just skip this part and get straight down to the product rule part of the section of the teaching. Okay, so let's have a look. So we've got dy over dx equals, sorry, that should be a t, important fundamental thing to do. Okay, so when I get that together, okay, dy dt equals, so what's the derivative of sine t? It's a nice easy one. It's simply cos of t. Then we've got a plus. Now the next term we've got here is 1 over t. Now we can't find a derivative of that in the form it's been given to us, so we need to convert it. This is where your laws of indices come in. So I'm just going to move over here to the right, make a bit of space. So 1 over t can be written as t to the minus 1. So laws of indices. Now we can work with that. So let's have a look. So we take the minus 1 down to the front. That's going to make this plus sign into a minus. Okay. Then we've got our t. Then we've got minus 1 as a power. So what's minus 1? Subtract 1 from it. Minus 1 is simply minus 2. Next term is a minus log of t. What's the derivative of log of t? Very simple, 1 over t. All these are standard derivatives that you can find in any table of derivatives. Okay, then we've got plus of the exponential e to the power t. So that's the world's easiest derivative, especially when there's no constant in front of the t, and it's simply e to the t, stays the same, no change. Okay, so that's the beginning. Let's have a look at the product rule. So this brings us to the formula, or the rule. So what we've got here is y, if y equals u times v, then we use this rule to solve the problem. What does that mean? Well, previously we were looking at an example of, we've used the sum rule basically, so you would have two terms together or subtract them. So that's the sum rule, nice and easy. You just treat each one individually as you come to it. With this one, with the product rule, they're actually multiplying one another. So you've got u times v, for example. So when two things multiply one another, the result is a product, hence the term product rule. Okay, so let's have a look at our formula. It may look as slightly complicated, but actually it's very easy. It'll make more sense as we do an example, but what we're going to be doing is we're going to be taking, so we've got u here, we've got u there. All it means is that nothing's done to it. This term here just means that you're going to find the derivative of v, so you're going to find the derivative of this v here, whatever that may be. Then you're going to add together the opposite. So if I just choose a colour, so now you've got v as it comes, nothing done to it, literally as it is out of the packet, times the derivative of u, so the derivative of this. Okay, that's all it means, nothing more than that. As I said, it's a lot easier to follow when we have an example, so let's have a look at an example. So I've put the formula over here on the right, okay, that we're going to use. So we've got x times sine x, that's what our y equals. So you've got a term that's our term we're going to look for, they're doing the derivative of, our variable is x. So we've got x times sine x, so it's multiplying it in other words. So we have to use the product rule. So let's have a look. So this here, which we'll designate as our, so I'm going to say that this here, that should be an arrow, can't control my own pen, is the u term. Okay, and this term here, the whole function sine of x, oh dear me, what's wrong with this today? Right, is v. Okay, so let's have a look. So we've got, whoops, dy over dx equals, so we just work from left to right with our formula. So we've got u is just x, so it's just x. How easy is that? Okay, then we've got the derivative of v is sine x. What's the derivative of sine x? Cos x. Still easy. Then we've got a plus sign. Okay, still easy. Then we've got v as it comes. Well, v as it comes is just sine of x. So sine of x it is. Then we've got the derivative of u. The derivative of u is, well, it's just x is u. Derivative of just x on its own is just 1. So I'm going to put that in. I'm going to put it in brackets to make it clear it's a multiply. Okay. Obviously that can just be written as sine x. Anything times 1 is just itself. So there you go. There you've got it, a final answer. So that's it. As simple as that. Let's have a look at another one. So this brings us to our next example, and the first thing I immediately spot that I need to correct is I'm missing a term here. There should be an x there. That should be 3x. Just try and squeeze that in. Okay, so working from left to right with our formula, got dy dx equals, so the formula says u as it comes. So there's our u, that first term. You can label it as we did with the previous example if you wish, but if you've got comfortable with it, you don't need to. 4x to the 4. Nothing done to it as it comes out of the packet. Times the derivative dv dx. So the derivative of 2 to the e to the 3x is, remember, you bring the factor, the coefficient down to the front and multiply it in. So 2 times 3 is 6. Then we've got e, and then the stuff above stays the same. Remember, this is a function. So in a calculator this would actually be written in brackets. Remember, the stuff in the brackets stays the same. So the next bit is a plus. Then we've got v as it comes. So this is a bit easier this time, because we just repeat what we've got there with the addition of an x that it should have had, my previous mistake. Then we've got du dx, so the derivative of 4x to the 4. Take the 4 down to the front to multiply it in, we get 16x. Take 1 from the power, we get 3. 4 minus 1 is 3. And that's it, it's done. Not much more you can do with that really. You could take out the common factor of the e and put it outside in brackets if you really wanted to. You might do that if you were trying to find what the gradient was at some value of x. It might be easier to put in your calculator, but to be honest, not really. Just go with it as it is. So now let's do a real world example, because this is what it's all about anyway. This is why as engineers we use calculus, so that we can solve real world problems. So we can put a man on the moon, or the man on Mars even. So we need to use maths as a tool, and that's what we're going to do here. So here we have an equation. Let me just get my pointer up. This here is an equation. Tells you the displacement of a spring against time. So you pull on a spring. So for example, it could be, say you've got, that's not a very good spring. Let's just erase that. And that's not much better. But say you've got a weight on the end of a spring, and you pull it down, and it springs back up, and it goes up and down, and it follows a sine wave, and you've got this exponential decay. That's the dampening of the spring and the air. Well, the air actually. So it follows this formula. Okay, so we want to know what speed it's doing in this particular circumstance If we've got this a was some constant in front, some multiplier that's 2, we've got a constant here for the k that's multiplying the time, which is 0.9, and then we've got a frequency of 5, so it's 5 hertz. So we want to know what velocity, what speed it's doing at 1 second. Let me just get rid of my terrible spring. Okay, let's have a look. I'm going to move this up a little bit, give myself some space. Okay, so first we need to solve it first. So we're going to do a differential equation. We've got dy, sorry, that's poor. First thing we need to give some serious thought to is, what are our terms? Well, it's ds. Okay, we're going to differentiate the displacement against time, and that's going to give us velocity. So the bottom term is going to be dt. Very important to use the right terminology. That means that our variable we're looking at in our formula is t. So anything without a t in it, which doesn't apply to either of these circumstances, but anything without a t would be just a constant and would disappear. But they've all got a t there, so we have to differentiate all of them. Okay, so this term here, that one there is our u, that one there is a v. Okay, so let's have a look. So it's u as it comes is the first step. I'm going to use, okay, straightforward, times the derivative of sine 2 pi ft. Now the first thing to mention here is, always in calculus we always talk in radians. Okay, so this term will always be in radians. It won't work in degrees. Additionally to that as well, we've got a pi symbol there, so that tells us within radians as well, and we've got t for time, which tells us within radians. So radians is a proper measurement system, unlike degrees, which is like a man-made way of understanding it. A useful one, but not mathematically correct. So within radians. So remember that. Okay, what's the derivative of sine 2 pi ft? Okay, well, if you remember the standard derivative, the 2 pi f, which is our k term, our constant term in front of the t, comes out to the front. So we're going to have 2 pi f, and then we've got our function, which, whoops, bear with me, that should be a cosine. Okay, cosine, ooh, dear me, cosine, and then the stuff inside the bracket stays the same, 2 pi f t, close bracket. Then we've got plus, okay, plus, and then we've got our v as it comes, so that's sine 2 pi, and then f t, so nothing changes inside either, of course, times the derivative of our first term here. So the minus k is going to come down to the front and become a multiplier. Now, so we'd have minus k times a, and then the rest of it. And again, this, nothing happens to this, stays the same. Right, important point here is I'm going to put this in brackets. And there's a very important reason for that, because if I didn't put it in brackets, it would look like I was subtracting this term from this, which of course is incorrect. We're actually multiplying. So I need to put it in brackets to show that. Now another important point is, you'll notice I've not substituted in any of these values. And the reason for that is this whole term here is giving us the generic solution expression, actually, that tells us, so we can substitute in for any time we're going to put in substituting for 1, but we can substitute in for any time or any values of constants, substitute them in and solve and find out what velocity we're doing at any point in time, whether it be 1 second, whether it be 1,000,000 seconds, 1,000,000 years. Okay, so that's why we do it. Then at this point, when we want to find a solution, then we start to substitute in. So we can simplify this a little bit as we go along. So we've got equals. Okay, so we're going to start putting values in. So A is simply 2. E. And then this is minus 0.9 times. Now I could have simplified this by bringing this to the front, but never mind. So we've got 2 pi here. Frequency, let's have a look. Frequency is 5, so we can just multiply that together. So we'll have here 10 pi. Then we've got a cosine function. Then we've got our stuff inside the bracket. So again, 2 pi 5, so that's going to be 10 pi. And seconds 1, so we can lose that. That's what happened to this second here, by the way, because it's just times 1. 10 pi. Close bracket, plus. Now sine 2 pi, so again, just simply change that to 10 pi. For 5 times pi, 5 for the frequency times the 2 is 10. 1 second. Let's put that in brackets. I always like to have brackets for my functions. And then this is our. So we've got 1.8 minus 1.8, shall I say? From our 2 times our 0.9 gives us 1.8 times our E. And then we've got minus 0.9. T, and T is 1, so I can lose that. Okay, so that would be our generic formula, we could say, and then we can put in any time we want and we'll get a solution for what velocity it's doing. Now our time is 1, so it's nice and easy for us there. Okay, now this is might look like quite a big lumpy thing to put in your calculator or do on a piece of paper or in your head, depending on how clever you are. There's some benefits here. If you look at this term here, let's just have a different colour. Let's have this yellow. This term here, this term particularly, is very relevant. If I was to plot this as a sine wave, let's just, right, very rough sine wave. Oops, like that. That value there would be 2 pi when within radians. So in other words, y equals 0. There's no value of 0. So the solution to that would be 0. 10 pi is if it continues going on and on and on until we get to 10 pi. 10 pi is still 0. Okay, so that means all that value there is equal to 0. Which means if I multiply whatever this gives me times by 0, all of this is 0, so all that has gone. Okay, so that helps a lot. Okay, just get rid of my awful sine wave. Okay, so all that is equal to 0. So I have to look at this side. Now this side can be simplified as well, because cosine, if I draw that, but I won't do it there, I'll do it here. Okay, that starts at the max, goes down, comes back up, and that point there is 2 pi. So in other words, it equals 1. So that means all of that there is equal to 1. Okay. So we've got 1 times 10 pi. So we've just got 10 pi. Again, so much easier. Let's get rid of that and that. Okay. So we've now got, if I simplify it, let's go down here. We've now got 2 times the 10 will give us 10. times the pi times the e times to the minus 0.9. Now that's, you've got to admit that is a lot easier to put in your calculator than all this up here. Okay, now if you put that in your calculator, you'll actually get 25.54 55. 25.5455 watt. Well, we're talking about speed or velocity. So meters per second is your SI units for velocity. So that's our final answer. So that it is how fast it's going at 1 second. 25 meters, 25.5 meters per second. Okay, and that is a real world example, and that's why we bothered in the first place. That's why we use calculus.